Hello students, I'm going to describe to you this week's assignment about simultaneous equations. So this is pretty much what I've written in the discussion assignment, but it may help you to hear it as well. So let's go through it. So the idea this week is that you're studying how to solve pairs of linear equations. They're also referred to as simultaneous equations, and you'll understand why in a few minutes as I go through this example. Now, one of the main uses for these types of equations is in finding out what are good trade-offs. A trade-off, as you may know, is you get one of something and then you want to get another of something else, and it depends on how much of the first thing you want versus how much of the second thing you want. So you can have more of the first thing and less of the second thing, and vice versa. Now, obviously, why can't you have more of both things? Well, because often resources are limited and there's a set constraint on how much you can have altogether of the two things. It may be money, it may be weight, it may be something else. Let's think about an example here. So let's say I have been invited to a birthday party and I go there and there are lots of goodies and I like cake and I like brownies. Now, because of the number of people there, somehow the host has made known that you can have 5 pieces of goodies, right? Some combination of pieces of cake and brownies, but not more than that. So I can have, say, maybe 3 pieces of cake and 2 brownies, or I don't know, 1 piece of cake and 4 brownies, whatever combination I want, as long as the number here is the total number of both items is 5 or less. Now, that should really be written as an inequality, but, we're just for simplification, I've shown that as an equality. So, okay, that's great. Now, very simple, straightforward. I can have more cake, which means I have less brownies, or I can have more brownies, which means that I get less cake, all right? But suppose this circumstance is a little bit different, okay? And in this case, I have gone to a bakery and I want to buy cake and brownies. But because I am on some kind of a diet plan, I cannot have more than, say, 8 ounces of this kind of material per day, which is half a pound, right? All right, now how do we do the trade-off between cake and brownies? Well, all right, what if I write the equation, my constraint equation, like this, where I say, well, I'll have a number of pieces of cake and I'll have a number of brownies. All I need to know is how much does 1 piece of cake weigh and how much does 1 brownie weigh. So then if I know this portion, right, the weight of a brownie and the weight of 1 piece of cake, then I can multiply that weight of cake by the number of pieces of cake that I want, and the weight of the single brownie by the number of brownies that I want. And I just need to make sure that the total does not agree 8 ounces. Now we'll be talking through this example a little bit more. And also the general approach to doing this is to define variable names. So what are our variables, right? So we talked about what? The number of pieces of cake, the number of brownies, and somewhere in there, the weights of each of those items as well. Now, because I know how to approach this solution, I'm simply going to say the variables are the variables, the things that we want to find out, right, is how many pieces of cake can I get and how many brownies can I get while meeting the constraint. So I'll call X, this is my first unknown variable, okay, the number of pieces of cake that I don't know yet what they will be, because that's what I'm going to solve the equation to find out. And my second variable is going to be Y, which I allocate to the number of brownies. Okay, so that's one part. Now I'll call the weight of 1 piece of cake A, right, and the weight of 1 brownie B. So you can ask, well, aren't A and B variables, right? Different kinds of cake may have different weights associated with each slice, or the slice size may be different or something like that. That's true. But in this case, we are not trying to find the weight of the piece of cake nor the weight of a brownie. We somehow already know that, right? What we're trying to find out is how many pieces of cake can I get and how many brownies can I get when the total quantity of brownies is not being measured in the number of items, which was the case in our previous equation, but this time the constraint is on weight. So what I'm trying to find out is how many pieces of cake can I get and how many brownies can I get when the total weight of them is 8 ounces or less, right? So, and I'll tell you how to approach the constraints in just a moment, but suffice it to say for now that the unknown variables are represented by small x and small y, and what are the constants? In this case, they're really the coefficients of the variables. They are represented by a and b. And if you follow this, oh, now what did I do? Okay, hang on one second. Okay, we're back. So with the definition of the variables and the coefficients as follows, I can write this equation. Now, this equation is exactly the same thing as this equation, right? Where the weight of one piece of cake is specified by capital A, the number of pieces of cake are specified by small x, and then you can read the rest of it. The constraint, remember, this is a constraint. It says I cannot have more than, or in other situations, maybe less than, of some quantity of the combination, right? This is a constraint. This m, the total weight of goodies that I can get, is a constraint on this combination, which is number of pieces of cake and number of brownies. Okay, that's important to realize. The variables here are the number of pieces of cake and the number of brownies, and it's their combination together that is being constrained. In this case, by weight, and not by the count of these things, right? We're not counting how many pieces of cake or how many brownies, which is what we were doing when I went to the birthday party. But in this case, what we are doing is we are measuring the weight of it. You know, the baker or whoever is behind the counter is going to weigh them out, and that'll be our constraint, okay? Sometimes if you go to a grocery store, and you can say, I want 2 pounds of hamburger or something like that, or, 2 pounds of cheese or whatever it is, or some other kind of edible, you tell them to approximate how much you're going to get. All right. So now let's carry on. We have an equation that represents the number of pieces of cake that I can have and the number of brownies that I can have, and that equation is constrained by the total weight of those two things. All right. So, well, that's straightforward, right? I mean, that's a simple trade-off. I can have, same as before, as when I was doing the count, I can have more cake but fewer brownies, or I can have less cake and more brownies. It's a trade-off between the two things. And that's it. Why do you need to do anything more? Well, all right, hang on. I run into a problem when I try to pay for this stuff, okay? So, I dig into my pocket and find out that I only have $10. Is that going to be sufficient? So now I have discovered a second constraint. It's not just the weight of things, which my diet allows, but also whether I can afford to buy as many of those things as I may want. So my first constraint was on the weight of the goodies. My second constraint is going to be on the total cost of the goodies. So now we're going to have two equations. Okay, so let's say I have only a total of $10. Now, let's say a piece of cake costs C dollars and one brownie costs D dollars. Okay, so how will I write this second constraint or the equation representing the second constraint? Well, actually, it's not that bad because you think about it. We were over here in the first equation, we talked about the number of pieces of cake and the number of brownies. And that's what we are still doing over here. We're talking about the number of pieces of cake and the number of brownies, but this time we also have to say, well, how much does one piece of cake cost, which is going to be represented by C, and how much does one brownie cost? And that's going to be represented by D. And these are going to form the coefficients of the variables x and y in the second equation, right? This x and y here in this equation, right, are the same x and y in this equation, that first one we had. In the first one, the constraint was on the weight of the combination here, and in the second one, the constraint is on the cost of the combination of pieces of cake and brownies. Okay, so this is important to note. We have the same variables in both equations, but each equation represents a different constraint, and the constraint is on a different characteristic of the things that we are getting. In this case, the characteristic is the weight of the thing, weight of one piece of cake or weight of one brownie, and the cost of the thing, so cost of one piece of cake and cost of one brownie, right? So we have two equations, we have two variables. And the two equations, each one of those equations is constrained. So we have two constraints, right? It was 8 ounces as the first constraint and $10 as the second constraint. Now, this count of twos, right? Two equations, two variables, two constraints, okay? So hopefully you've got that clear now, all right? Now this portion over here basically just says in text what I just told you about, but okay. But here's something that is important and that is worth spending a few moments on. So I just flowed along this thing in our discussion earlier, but there's something that may strike you as you're working on your own problems of this nature, which is, okay, that's great. We have things. In this case, we are trying to figure out how many things. So it's the count of things that we're interested in. Number of pieces of cake and number of pieces of brownies, right? But then our constraints are not on the count. They're on different characteristics of the thing, right? So the thing right now has 3 characteristics that we have identified so far. There's the count of a particular thing, how many pieces of that we have. There is the weight of one piece of that thing, and then there's the cost of that piece of thing, right? So there are 3 characteristics that we're dealing with over here, which is the count, the weight, and the cost. This is not something that you need to be worried about. It just sort of arises naturally out of a good problem. Now, why did I say good problem? I said good problem because it's possible to use this form of the equations and come up with not so good problems, which would be of the type, oh, I bought 1 coffee today and 2 muffins, and that cost me M dollars. And then the next day I bought 2 coffees and 1 muffin, and it cost me N dollars. And it's like, what? This is not even worth writing out the problem, right? Because how is it that, I didn't know what the cost of the coffee and the cost of the muffin was when it's written right on the board, generally in every coffee shop that's done. So don't come up with problems where you know the values of the variables up front. Try to create a genuine problem or set up a genuine problem where you don't know the values of the variables in advance. And that's what you're trying to find out. Not only will you learn more, but that is going to be a more satisfying situation. All right. So let's get back to our problem, right? So we are interested in the counts of the things, but our constraints are on the weight in one case and the cost in the other case. So how is the count connected to the weight and the cost connected to, again, the count of things, right? And that's, you may realize this already, but I want to emphasize this again. That's the role, the connection or the glue that, or transformation piece of magic potion that turns the count of the things into the same type of variable, such as the weight or the constraint, are these coefficients, right? A and B and C and D, right? The A was the weight of one piece of cake, B the weight of one brownie, and then C the cost of one piece of cake, and D the cost of one brownie. So when you multiply the count of the number of pieces of cake by C, you get the total cost of the cake. And when you multiply the count of the brownies, which is Y, by D, you get the total cost of the brownies. And the sum of that cost, the total of the totals of the cost of cake and brownies, as you can say, that sum of all the things together is represented by this equation. Now, we only have two terms in this equation because you're only dealing with two things. But if you extend the thinking, you can see that we can have many more variables, in which case we'll need many more equations and the constraints that define those equations. So solving a pair of equations enables us to deal with two variables. If we want to deal with more variables, we'll have a set of 3, 4, 5, whatever number of equations that we want. So let's have a quick recap. We've got two things, pieces of cake and brownies, which are represented by the variables x and y. And we want to find out how many of each type of thing, number of pieces of cake and number of brownies we can get. Okay. Now you may be setting up a problem where you're not interested in the count of the things. Maybe you're trying to figure out how much gasoline or oil you need to put in your vehicle, right? And then that's weight. Okay. That's not a count. Okay, so you may be able to constrain the weight in some fashion. I'm not making up the problem, so I don't know yet, but this is what I would like you to think about. The key piece to note over here is that the unknowns are something that you need to identify up front. What is it that you're trying to find out? Okay, I want to find out the number of pieces of cake and the number of brownies, right? It could be the number of oranges or number of apples, or it could be the weight of oil and the weight of gas. Identifying what it is that we're trying to find out is really key. If you try to set this up without having clear in your head what is it that you're trying to find, you're not going to be successful, and you're going to get very frustrated in trying to set up the problem. So students, I see this all the time. One of the mistakes they make is they don't define their variables up front. You really need to write it out like this, right? What are your variables? You need to define them explicitly and write them out. Okay. Then the other piece to note, which is implicit here, any of these equations, it doesn't matter, is look, each term of this equation has the same units as the constraint. The units means, the units you use to measure the things, right? So in measuring the count, you just use numbers, but that's not what our constraints are on. Our first constraint here is on the weight. And so if you think about this, M was 8 ounces. It's a unit of weight. The ounce is a unit of weight. I didn't use grams because I didn't know how familiar you are with those or not. But anyway, this is a unit of weight over here. And then you look at this term, and you'll find out that each of these terms actually is also in the units of weight, because you have, let's say you have 2 pieces of cake, and each piece of cake weighs an ounce. So now you have 2 ounces. So the units of this term are 2 ounces, and the units of this term, maybe, 4 ounces or 6 or whatever it is, right? Depending on the weight of the brownies. But the key piece over here is that the units of each of these terms is exactly the same as the unit of this constraint. So if this is expressed in ounces or in terms of weight, then this term is also expressed in terms of weight, and likewise for this term here, the first one. And here, if the cost, this time our constraint is on the cost. So N is in dollars, right? Money, or pounds or rupees or what have you, right? But again, the important piece is that each term has the same unit as the constraint. So if this is in dollars, this is also in dollars, because one piece of cake may cost $1 and one brownie may cost $2 or whatever it happens to be. So if you have set up your equation and the units of measurement, so to speak, are not the same for each of the terms and the constraints, something has gone awry, right? Something is mixed up, confused, or wrong. Okay, so you need to go back. So the simple approach to this is be very, very clear about what it is that you're trying to find out. Okay, be very clear about what the constraints are. Okay, what are the limitations? In order to get there, you will need to know what are the combinations that you're trying to constrain, right? So in this case, you're trying to constrain the combined weight of the things. And in this case, you're trying to constrain the combined cost of the things, right? So if you know what you're trying to find out, you know what you're trying to constrain, and you have then identified the constraints, the quantity or the number associated with the constraints, you're almost there. One other piece that you need to think about, and this can trip you up, is, well, how is this, the unit in which I am measuring the thing may not be the same unit as the constraint. So here we were using the count of X and the count of Y, right? But my constraint over here is in dollars. How do I connect those things together? Or, back here, up here, the constraint was in terms of weight, but we were still measuring X in count and Y as a count. Right. Remember, I said earlier that these are the coefficients that serve that connection glue, right? So the coefficient will connect the count of the thing to the weight of the total of that thing that you got. So your X is a count and A is the weight per piece, right? Per single count, okay? And likewise for B. And similarly here, X is the count and C is the dollar cost for one count, one single piece of cake in this case. All right, you've got it over here. Now you're all done, right? This is it. You can solve these two equations by using the methods that you have learned in the lecture videos, and it will be all good, right? Here's a calculator, not a calculator, really. It's a graphical technique for solving pairs of equations, and you can try it out, or I'll make another video later and maybe share that with you. But I also want to go back to saying why we call these simultaneous equations. You see, we're trying to find out the count of these things subject to two simultaneous constraints. It's not just this, like say, okay, I can trade off how much, what pound of, how many pounds of or ounces of cake I can get versus the number of brownies I can get, because I can always make that trade-off. It's pretty easy, right? My total constraint is this. I can increase one, decrease the other, and so on and so forth. But this is the important point. I simultaneously have another constraint on those same two variables, X and Y, and this constraint is in terms of the cost. So I can't arbitrarily trade off the number of pieces of cake against the number of brownies just because I'm only satisfying one constraint, but now I have to simultaneously satisfy a second constraint. And that's why these types of equations are also known as simultaneous equations. Okay, so hopefully you were patient enough to listen to the whole thing, and there was a lot of repetition in it, but it was good for you to hear the same thing over and over again. However, if you still have questions, don't hesitate to contact me. You can paste your questions to the forum, or you can email me directly. My email address is given in the forum. All right, good luck, and come up with some creative problems, right? Not those sort of tepid, kind of a waste of time problems. It's going to be a waste of your time, and I don't enjoy reading those either. So use your imaginations and come up with something creative. All right? See you on the forum. Bye now.